Welcome to Stochastic Processes. This is a course that I gave the last time about 15 years ago to theoretical chemistry graduate students. This course will be based upon a couple of textbooks, mainly this one by Gardner and this one by Van Kampen. And there's also a new textbook, which I'm reading right now, which is very good. I'm going to share that with you. Let's see, share screen. There's that. Open it, I guess. There somewhere. Oh, it is. Okay. Here it is. This is called Stochastic Energetics by Ken, there's his name, Ken Sakamoto. All right, so let's get started. I'm going to share whiteboard here. Oh, wait, that's not the right one. It's the other one. It's not the whiteboard. So we're doing stochastic processes. And we're going to start with Einstein's diffusion equation. And so we'll just some backing up. This is really non-equilibrium statistical mechanics. It's a component of that. And there's two components of non-equilibrium statistical mechanics, or mathematically, there's two ways of doing things. There's distribution equations, or distribution dynamics. And then there's individual processes, or individual trajectories. The distribution dynamics considers distributions of trajectories. So we're going to begin with the Einstein diffusion equation, which is an example of distribution dynamics. Okay. So what Einstein was doing was trying to explain Brownian motion. So we start with Robert Brown in 1827, observed the jiggling of a pollen grain in a fluid, suspended in a fluid. Now, apparently, Robert Brown did not really observe Brownian motion, because in order to observe Brownian motion, you have to be really, really careful and isolate your system from any vibrations. So if somebody's pushing a cart down the hallway, there's going to be vibrations, and that's going to cause my pollen grain to jiggle. So Robert Brown did not take sufficient precautions to prevent the vibrations from interfering with his experiment, so they probably did. But nevertheless, Brownian motion is a thing, and it can be observed, and Einstein explained it. And this goes back to 1905, by the way. That's an important year. That was Einstein's miracle year, where he published 4 papers, 2 on special relativity, 1 on Brownian motion, and 1 on the photoelectric effect. He won the Nobel Prize for the photoelectric effect. And of course, special relativity, well, that was revolutionary. And then there was this paper. And this paper was also important because apparently this was a watershed point where physicists finally accepted the atomic model of matter. Chemists at that point probably all accepted it because chemistry doesn't make sense without it. I mean, I'm not sure what chemistry would mean, but Ernst Mach was a famous physicist at that time. He specifically argued that it was only a model, and that there might be some other deeper theory of matter. He was kind of right about that because, of course, we have quantum mechanics, but he wasn't entirely right in the sense that it turns out the mechanics of particles, atomic particles, does explain all observed macroscopic phenomena. Well, if you had gravity as well. Okay, so that was an important year. So a champion of the atomic model at that time would have been Boltzmann, and then this Ernst Mach was on the other side. So, but after 1905, after Einstein's paper, physicists essentially all accepted the atomic model of matter. And then, of course, things happened pretty rapidly after that time. And we ended up with quantum mechanics by the late 20s. Okay, so let's begin with Einstein's model. What did Einstein do? Well, he supposed, so this is the Einstein model. He supposed an initial distribution of particle positions. So this is where we get into distributions. So we'll call that f of x. X could be a 3-dimensional vector, but we're going to treat it as 1-dimensional for simplicity in doing the in our discourse. Because this is the initial distribution, we can call that f of x 0, and that's time equals 0. And so there's going to be some kind of dynamics, a jiggling that we're talking about, and the particle gets a kick, or gets kicks, and moves in time delta t. So we discretize time, which is typical in, well, certainly in any kind of numerical work. So we consider a time step delta t, and then the particle will move, and the question is, where did it go? And so we assume, so this is one main assumption, assume Markovian process. Which means the movement, particle motion, movement depends only on where the particle is. Particle's position in the previous step. Not on previous locations, that is, before the current time. This assumption can be relaxed, and we will consider such relaxation of the process later on. Move it to the other way. Yeah. So this will be the particle position at time delta t. The distribution. Actually, if we take that and multiply by dx, this is the probability particle is in x to x plus dx at time delta t. And that will be equal to the integral over all step sizes possible, okay, times the distribution of steps in the time delta t. So that does depend on delta t, but I'm not going to make that explicit, times the probability. Oh, I didn't do that right. That's fine. Correct that. So if the particle's at x at dt, and it made a step of delta, then it must have been at x minus delta at time 0. And then I'm going to multiply that by dx, so that this is the probability particle is in x minus delta to x minus delta plus dx at time 0. Now, of course, I'm going to cancel the delta, the dx's, because we just want an equation for the distribution, but I just wanted to make sure that we're all on the same page with respect to the definition of these distributions. So we end up with, okay, so I'm going to do that, but I'm going to insert Taylor expansion in time and space for f of x t. So for example, we have f of x delta t, that will be equal to f of x 0 plus d by dt of f at x. This is with respect to time, but then I'm going to evaluate it at 0. So that's what that means. Take the derivative with respect to time and then evaluate it at 0. And then we have times delta t. But we also have f of x minus delta at time 0. And that's going to be equal to f of x 0 minus the derivative with respect to x of f evaluated at delta equals 0. Well, it's the derivative of x minus the function f of x minus delta with respect to delta, which is the same as taking the derivatives with respect to x and putting a minus sign. So that's what at delta equals 0 times delta. There's your step. And then we have the second derivative. That's going to have a plus sign and a half in front, because the second derivative with respect to delta is the same as the second derivative with respect to x. And of course, we evaluate at delta equal to 0 and time equal to 0. We get a delta squared. Okay, so there's extra terms here. We truncate extra terms. Okay, both in time and space. So the idea is we're assuming that the time step is small. And because the time step is small, the particle can't move very far either. So delta t and big delta are both 0. Or that is to say, sorry, not 0. They're both small. And so we can justify these series. So we substitute those in and into the equation that we had above. This one, which I can call equation 1. And we get f of x0 plus. There's going to be a delta t in front, and we're going to have the derivative of, so we're going to call that d. I'm just going to simplify my notation. That'll be my first derivative with respect to time. That's going to be equal to, well, we have to do that integral. So I'm going to plug in the Taylor series that I have above here. So I'm going to have the integral with respect to delta, 5 delta, f of x0. This has no delta in it, so this is just going to be the integral of 5 delta. Next term, integral 5 delta times delta times the derivative with respect to x of f. And that, again, has no delta in it, but there was a change in sign. There was a minus sign here. So I'm going to put a minus sign here. And then we have a half integral, again, over delta. We have 5 delta times delta squared. And then we have the second derivative of f. Again, there's no delta dependence in this factor. So what do we have? So this integral is equal to 1. The particle must move somewhere. That's a normalization. This integral is equal to 0 because we assume that phi of delta is an even function. In other words, I'll write that out like this. So positive and negative steps are equally likely. Phi is an even function. And equivalently, we say the step is unbiased. And now we have this extra term here. We have a half integral with respect to delta. Five delta squared. So this is the second moment of delta in this step. And then we're going to set that equal to d delta t. So there's a bit of sleight of hand here because we're already assuming that it's proportional to delta t. And I guess Einstein probably already expected that to be the case. What are the alternatives? We go back and look at this. Well, first let me substitute this in, and then we'll think about what would happen if it was something else. If this didn't, well, one thing we can say about this for sure is that if delta t is very small, this has to be small, because if delta t goes to 0, the particle doesn't move, and this has to be 0. So what could happen? So you could have powers of delta t that are less than 1, or powers of delta t that are higher than 1. If we have any powers of delta t that are higher than 1, they'll cancel out. They'll go away when I take the limit delta t goes to 0 for our equation. Anyway, what do we have so far? So we have those. The first term is f of x0. They're going to cancel out. Let me just go back and show that. So we have this term, and we have this term, and they're going to cancel out because these two things, well, here it is right here. This term and this term are going to cancel. So let's do that. Cancel. Whoops. Cancel. Cancel those terms. So our equation now looks like this. We have the time derivative of f x0 times delta t. That will be equal to, we've got rid of the first term. The linear term goes away for the delta because the delta step is even. It's unbiased. So we end up with d delta t times the second derivative with respect to x, f of x0. And so the delta t's cancel. Now, if this had been higher order, power of delta t, then it wouldn't completely cancel. And then if you made it delta t small, those terms would go away. If we had a lower power of delta t, then this term would be zero in comparison. Another way of thinking about it is if we simply divided by the delta t, if this power of delta t were lower than first power order, then when we divide by delta t, we'll get a negative power of delta t. If delta t is really small, that's really big. So we get a function that the distribution function changes discontinuously in that case. So this is the only case where it changes continuously, and this will turn out to be the correct description. So let's just go along with this now. So we get our Einstein diffusion equation, E2. So we have d by dt of f of 0, x0 equals d second derivative. This is the Einstein diffusion equation. And b is the diffusion constant. The diffusion coefficient units equal, well, what has it got to be? It's got to be per time, and it's got to be distance squared. So distance squared per time. Okay, so what are we going to do next? We're going to solve that equation, of course. We're going to solve using Fourier transform. With respect to x. So I'm going to define f tilde of xt as the Fourier transform of f. Well, except that this is now going to be a function of k. I should change that. So this is now a function of k. And Fourier transform with respect to x, e to the I kx and f of xt. So this is a normalization factor, which is convenient. It makes it symmetrical. With respect to the inverse transform, I want that, I want this. Okay, so we're going to substitute that into the equation 2, the Einstein diffusion equation. The time derivative is unaffected. There's no time integrations here. So we have the time derivative of the Fourier transform of the distribution of positions of the particle is equal to, and then we have the diffusion coefficient, and then we have the Fourier transform. of the second derivative with respect to x of f of x t. Okay. So what we're going to do is we're going to do integration by parts twice. And when you do integration by parts, you get a boundary term minus an integral where you, well, we have these derivatives here, and we can swap this derivative over to the other side, over to the other function. So we can do that once, and then we pick up a minus sign when we do that. We also have a boundary term, but the boundary terms are going to be 0. I'll come back to that. So we just have a minus sign from the change from the first integration by parts, and then we have another minus sign for the second one. So altogether we get minus I k, because we have to take the derivative with respect to that twice and apply minus signs, squared d 1 over the root of 2 pi So I've taken the derivative with respect to x twice and pulled out the constant factors. And this just gets us back to the Fourier transform of f itself. So I square this, it's going to give me minus k squared. There's a d there, put that. And then what's left is the Fourier transform. T. Okay, so we've simplified our equation significantly. Oh, boundary terms, why are they 0? So this is true because f of xt is localized, which means it goes to 0 as x goes to plus or minus infinity. So those are my boundary terms. And also, if it goes to 0, then so does the derivative. Because if it's 0 at infinity, well, that's 0 is flat. It's got 0 derivative as well. So we end up with this simple equation we can solve. That's the differential equation whose solution, it's a well-known one, is an exponential function. So we get an exponential function with respect to time. And so that'll be e to the minus d k squared t. And that will be times the initial Fourier transform of the distribution function. Okay, so there's our solution. It's in it. First order, it's its initial value. There you go, solution. So now inverse transform to get it in x space. So we have f of x 0 equal to, so for the inverse transform, we have the same normalization. That's why we chose it, so it will be the same, symmetrical. We integrate now over k, and we have e to the minus ikx. There's our inverse transform of this function here. So we have e to the minus dk squared t times f tilde of k0. All right. So, and this, of course, in turn, is just the Fourier transform respect to x, that's ikx fx0. Okay, so what we're going to do is we want to do the k integral. Actually, this has to be an x primed because we already have an x here. This has to be a dummy variable, x primed. So we get 1 over 2 pi. So we got the root of 2 pi is twice. I'm going to pull my integral with respect to x primed out here. And then I've got the integral over k. This looks like this. It's got the dt k squared. And then we have plus ik x primed minus x. And then finally we have f of x primed 0. So we're going to write this in this form. Call this g of x. Actually, I want to call it g of x minus x primed. And this is a convolution. Fourier come, and then this is the is called it's the kernel of the general. I guess I don't need an uppercase letter. It's the kernel of the propagator. This is the time propagator for the diffusion equation. And it's also known as a Green's function. Or Green function. So what is G? No, I don't want this. Okay. G of x is equal to 1 over 2 pi integral over k of e to the minus dt k squared. Okay, back at the equation. Okay, so I actually wanted it as a function of x minus x prime, so I can go back and edit this part to make it better, closer to what we end up with. Just do that. Okay, so it's going to be minus. And this is x primed over here. So I'm just going to replace this by x. Now, notice I factored out the dt here in the exponent with a minus sign. So that means I've got a plus here, and I've got x, because now I've replaced x minus x prime by just x. I have to divide by dt. There's a k. So what I'm doing is I'm anticipating that I want to complete the square. Actually, I'm going to do that right now. So if I add in here 1/2 of this squared, okay, then this is now a perfect square. But of course, it wasn't there, so I have to subtract it back out again. And I'm just going to put that in another factor. I'm going to have another one with a minus sign here, but none of these. And so I have minus minus. So I'm going to get, and there's a dt over dt quantity squared. So you end up with a plus. Okay. No, yeah. We have to put in a minus, but there's already a minus there. So we get a plus. And we have x squared. I know what I did wrong. I made a mistake, but we're going to fix it. Okay, I left out the I. There was an I here. And so when I square that, I get a minus sign here. And then this one will have a minus sign. Right. And then I've got my 4, that didn't change, but my dt, well, one of the powers of dt cancels, and we're left with that. Okay, good. And this part doesn't depend upon k, so it can actually factor out. But I'll put it over there for now, because I want the 2 pi to go with the integral. This becomes this. Sorry, that's not squared there. So this thing, when you square it, you get all of this. That's the idea. Oh, and then of course I still have this factor, which isn't part of the k integral. So this integral here is a Gaussian integral. And let me just show you, let's share the screen because I got it ready to go. Gaussian integral. Here it is. This is Gaussian integral formula, which if you've probably know that, but if you don't, this is Wikipedia. So you've got a nice derivation of this formula. And then you can do a change of variables, so you can generalize and get this formula here. So that's kind of what we have, except our b is imaginary. You still get the same answer. You can justify using contour integration. So we're not going to do that right now anyway. So we're up to here. And this integral is just pi to the 1/2 times 1 over dt. So, or dt to the -1/2. So altogether, what do we have? We still have a 1 over 2 pi in front. D of x equals e to the minus x squared over 4 dt, and dividing by, it looks like, so I got a 2 there, which is the same as the root of 4. We have a pi, but we've got a pi to the 1/2. So we're going to get a pi to the -1/2. So we end up with 4 pi dt to the 1/2 in the denominator. And so this is the green function for time propagation of well, this is really a function of time as well as space. So I should really be making that explicit. Okay, and so we can go back and substitute that into our general expression and get the full solution to the diffusion equation for arbitrary initial conditions. We get our distribution at time t is equal to the integral over x primed. Now we can go back and put x minus x primed in here. That's multiplied by f of x primed and times 0. So this is our propagator. It tells you how to change the initial distribution into the final distribution after time t is elapsed. Then in particular, suppose we know the particle is at x naught. At time equals 0. That corresponds to f of x0 equal to a Dirac delta function, x minus x naught. And if we plug that into the above equation, then the f distribution at time t will just be equal to this propagator, the kernel, except with x primed replaced by x naught. So we get a Gaussian distribution at time t with width equal to the square root of this. This is a Gaussian e to the minus sort of a delta x squared divided by sigma squared, or sometimes 2 sigma squared, depending on you find it. But we're going to be loose with the width. We're just going to use the square root of 4 dt, which equals 2 times the root of dt. So the width is increasing like the square root of time. Or alternatively, you can see the variance of the Gaussian, which is like the width squared, goes linearly with time. And that's consistent with Einstein's assumption that this integral way up here, there we go, it's way back here. Yeah, that this is linear with the time step. So that persists. Oops, I won't do that. Okay, what's next? Yeah, so we're going to be more explicit now and characterize the width explicitly, whether I'm just assuming you know that. So the width will be defined as the average of the deviation. The average of x minus x naught squared, which, by the way, can be written as the average of x squared minus the average of x squared, because x naught was equal to the average of x. If you just expand this out and use the fact that the angle brackets are basically distribute across the terms of a sum, you'll end up with this. Okay, so we need to work out what this is. This is simply defined to be the integral of over x of the distribution at time t, because this is time t. Okay, that's not explicit here, but there is a time dependence because the distribution is varying with time, times x squared. So we're basically getting the second moment of a Gaussian. Actually, okay, so the simplest way to do this is really going to be we work directly with the original definition. And then we can replace x by x minus x0, change variables, and get us to this form here. Oh, it's next integral. E to the minus dt. Sorry, because that was the other one. E to the minus x squared over 4 dt. This is a normalization. And then we have x squared. Of course, that's a standard integral that will be available on Wikipedia, but I thought this would be a good opportunity to illustrate the Feynman's integral trick, if you don't already know that. Which so let I of alpha be equal to the integral of e to the minus alpha x squared. And then note that if I take the derivative with respect to alpha of I of alpha, I get minus so I take the derivative of this integral with respect to alpha. I'm going to get a minus x squared come down. So there's the minus sign. Here's your x squared. Okay, so that's fine. So, but the thing is, we already know what I is. That's the Gaussian integral that I referred to before. We know that that is equal to the square root of pi over alpha. Well, I'm going to write it like this. I write it pi to the 1/2, alpha to the minus 1/2. And then, so this is going to be our desired integral in here. So our desired integral is now equal to so I say I just want to look at this. Yeah, this is this integral. Forget the minus sign for now. Okay, so that's equal to minus the derivative with respect to alpha of I of alpha which we know to be I pi to the 1/2, alpha to the -1/2. We get pi to the 1/2. And then we get -1/2 come down with this minus sign, so you get a half. And then you get alpha to the -3/2. Okay. So if we sub in, what alpha is. So this is the integral trick, and this was the integral we wanted to do here. Well, we have the answer. Okay, we know what that is. So the root mean square deviation from the average x equals square root of this average that we're doing. So that's, I'll call it to the 1/2. So we have to do the integral up there to the 1/2. So we had the numerator was pi to the 1/2 over 2, and it's alpha to the -3/2. So what is alpha? It's 1 over 4 pi dt. So we get 4 pi, well, it's just 4 dt. The numerator had the pi. There's no pi there. Okay. And because it was 1 over, we just have 3/2 power. Okay, so get that. And then we have the denominator that we had above. The color I was at. To the 1/2 power. It was a denominator here, and it was 4 pi dt. So what do we end up with? Okay, so we're going to oh, this was actually to the 1/2. That's better. Okay, so the pi 1/2s cancel. I knew that would happen. And so we get 2 here. We're going to get a 2 down here. We're going to get a 4. Well, wait. So this 4 dt is going to cancel one of the 3 root of 4 dt factors that appear here. So that's nice. And the pi's cancel. We got that. So we get a half. That didn't cancel. Times 4 dt, which is just 2 dt. All to this. Okay, I'm going to left out the square root. So we see that the particle typically moves about at the rate of, like, it goes with the square root of time. That's how a particle. This is a free particle. I've imposed no boundary conditions here. It's just like a particle jiggling in some kind of a viscous medium. Otherwise, there's no boundaries. So how do you go beyond this? So we've said all we're going to say about that particle. The diffusion equation can be solved with boundary conditions. These are maybe different from the ones that you've seen before with other equations. So there's two kinds of boundary conditions. We could have particles bounce off the wall. So in that case, the boundary condition is that that the derivative f of x at time 0, or I'm sorry, at all times, it's a boundary condition, would be an initial condition if it was only at time 0, that this is equal to 0 when x equals boundary. Or if this was if we were in multiple dimensions, then we'd have like an n vector dotted with the gradient of f of x. This is now a vector. That equals 0, when x is on the boundary and n is the normal to boundary. And then you can also have particles escape or absorbed. Or react, in which case they become other particles, but that would be another distribution. So in this case, our boundary condition is that f of x of 0 equals 0 on the boundary. And then you could do this, and there's a book which I want to mention. I should have had it ready to go. Hopefully I can see it easily. Where is that? It's here somewhere. Well, it doesn't matter. I'm just going to tell you the name. Crank. Anyway, there's a book called by Crank, Diffusion Equation. I think I have the name of it written here. Book. Mathematics of Diffusion. Very good book. It has a lot of different examples. So I'm going to stop there. That'll be our first lecture, and I'll carry on with the next one.